here. Great. So before we go into the talk, it is customary for us to ask the speaker, what does compassionate math mean to you? And here is the question for David. David, what does compassionate math mean to you? How does this word resonate for you?
Thanks, Priya. Thanks for having me here. We were talking before this started, and Ted said that mathematics is basically like technology for learning, which makes sense to me, or remembering what's going on in the world or something. So if math is technology for learning, and compassion is for me something like appreciating loss, not liking it, but understanding deeply what loss really is, then maybe getting lost in mathematics, for example, is something that happens. So compassionate mathematics would be that in this technology, for learning, we take account of like when people are getting lost, and we care about that. So I think that might be what it is to me.
Thank you so much, David. Like, I really enjoy doing math with you, and I have seen that care when we do math together. So thanks for that.
Thanks.
We are ready to go into the talk. If you like, for the audience, like if you have any questions, like you could raise your hand or like find a moment to barge in and ask questions. David, would you be comfortable with that?
Yes, please. The more participation, the better, I think. So
awesome.
Yeah.
Thank you so much, David. Okay, so here we are.
Sure. Okay, so I want to talk about the Yoneda lemma and how the Yoneda lemma applies. Basically, I think that we can use math to track things that we care about. When we care about something, we need to tend to it. We need to pay attention to it. Think about something you care about, whether it's a baby or someone who's dying, or a garden or anything, that you attend to it. You pay attention. You think about it, and you might need to track things like when they need to eat, or when they need to be watered if it's a plant or whatever. And tracking all those variables, it's not like it's math. It feels like math, but it is something that we need to track. And so tracking things is more in the realm of math. And so we can use math to track things we care about, track what we care about. So Yoneda lemma is really about making generic objects within a realm that we care about. It's about how generic objects work in arbitrary spaces that we track. So what I need to start this is like maybe a volunteer of somebody who has something concise that they could say they care about.
Okay.
Say?
Okay, I care about.
What do you say?
I care about endangered species in this world. Is that generic enough, or do we need something better?
Yeah. So what I need to know is, if you care about that, what are you tracking? Like, what could you pay attention to? Various things that you would record. You'd write them down, and you'd say, kind of keep track of them. Can you think of anything like that?
Yeah. I would care about their population numbers, how it is changing over time. Like, are they becoming better? Are they going closer to extinction? That's something I would like to know over time.
I see. So then a species, and then you have like number.
Yeah, and growth, decline.
And then you have like every species has a population, a number, and then like you could have two numbers, like A and B, and A would be that one, and B would be that one. And then we could have like a number that is greater than another number, a number A greater than B, numbers A greater than B. And then we could try to check that. So given numbers A greater than B, we do have a number, right? We do have two numbers. So given two numbers, a greater than b, we have two numbers, each of which is a number. And it's kind of like maybe a little bit strange, but we could say like a species 2 times a species over a time interval. So if you had a species over a time interval, you could have a species, and you could, at each time, maybe I need to say that, a species at a time, and given a species at a time, you get a species, but given a species at a time interval, you get two species, and this diagram commutes. What that means is if I take my species and I look at this over a time interval, and I see what species it is, and then I look at the 2 times, and each one of them has a species. Those are all the same. Does that make any sense? Did that parse? That this diagram, all the arrows in this check mark part commute? Meaning that if we start with a species over time interval, we get a species at 2 different times, but they're the same species. But a species at a time has a population, I think. Instead of the species having a population, the species at a time has a population. So as I learn about this model that you have of the world, which is not just yours, a lot of people think about this, but you're right that, I mean, I'm thinking of it as your model. We can start to track that a species at a time has a number, and therefore a species over a time interval has 2 numbers, namely at the left end point and the right end point of that interval. And you want to know, like, we're happy, so Priya happy is like the pullback, maybe, of this, which says that Priya is happy when there's a species over time interval such that the numbers, or it's not a pullback, I'm sorry, if it factors through, no, it is that. So this is all species over time interval where the 2 numbers of their population at the left and right of that time interval, that the first one is smaller than the second one, or something like that. That the population is going up, or something like that. So this might not be exactly what you said, but I'm kind of trying to say, like, we could start to track the situation you're talking about by a bunch of sets and functions. And that's the next thing, is that given one of these pictures, this picture is a picture of a category, and a functor from that category to set is a way of filling each of these concepts, the concept of species, the concept of number, with a set of possible things that means. So when we think of a number, question?
Yeah, David, like Tim has a question here. Like, so he says, does the quality of life of endangered species count? Because he's thinking increasing populations in zoo is less good than increasing populations in the wild.
Yeah, great point. So what I call these things ologs. I at some point was hoping that, like, maybe the world could, like, people could, like, log their ontology of the world, and that ontology would constantly be changing. So it'd be like a blog instead of like a fixed ontology for all time, where you might try to say, like, what's the actual ontology of the whole world or something, whereas I think really we're constantly changing it. And so if we talk about endangered species, maybe we're talking about populations or the population growth or something, or maybe that's what I thought you were talking about. But then as we think more, it turns out Priya isn't happy here. Priya is happy when, like, the quality of life goes up or whatever, and we start to change this olog, and that's perfectly fine. And one thing about category theory is the ability to map between different ologs or categories. So if we wanted to include quality of life, then you'd start to have to define what you mean by that if you want to actually track it. If you just want to look at them and say, I have happy feelings when I look here and I have sad feelings there, then you would track your happy and sad feelings. But if you say, no, it's about how well they're eating and how much space they have, then you can track all those things. So the way you're tracking everything, the concepts are this C, and that's the concepts. And then, like, the examples we'll get to in a second, but I think there's another question. Was there a question, Priya?
So I was gonna ask, like, if we want to update this olog, would it be like a separate concept box, or like about the quality of life, or would we be adding these concepts to this olog to update it?
It's up to you. I mean, so you could say like an animal. An animal has a species. I don't know. Does an animal have a species? An animal is of a species, but then the animal has like a mood or something.
Mm.
And then we could take like a happy mood and then take the pullback here, and this would be all the animals with the happy mood. I know I'm kind of drawing like nuts now, but that's what OLOGs kind of do when we start to add to them. So they start to grow, and you could make a whole new one, or you could add to it, but we could start to look at all the animals that were in a happy mood at a given time or something like that. So we can start to track all this. So we could look at species, a species, and then every species has a population or a species at a time. And I think at a time and has population at time. And I'll move this number thing over there. Okay, so we could say, all right, we have species, like in our database, we have like some weird, number, and it says and it's like and then it's like species name, which I didn't write up there, because I wasn't tracking that. But the species name is bonobo or something. And then at time, like 2024, has population 17 or million or whatever. I don't know. And then like we have like 612314, and it has like species human 2023, and it has like 8 billion or whatever. And so we could just start tracking all of these things and look at species over pairs of times and see when the numbers are decreasing or increasing. And that would be this tracking that we're doing of the thing we care about. So whoever is thinking about endangered species has a much better model than this thing. They are tracking much more interesting and important variables in more organized ways. But this was just like very quick. And the point is that like we're going to be able to track this stuff by having our concepts laid out and then having our examples in a database that concept web tells us about. And we can update it. And where we're going with this is that like when we look at these examples, E, we can apply E, given our example set, which is all this data here, we can apply E to species at time, and get a set. And that set is like, 516117 and 612314 and all we're like, well, those numbers don't make any sense, but because they're just random numbers maybe. But once we like look at where they go in, we can take functions of this thing and get like actual numbers like 17 billion and things like that. Does that make sense? Like what I'm really saying is that the examples might not be like the set of examples might not be in this kind of formulation might not be meaningful, like the labels on the set, but like we can get the meaning by looking at populations or other parts of this thing that we do understand, like number. I don't know if that tracked for people.
Question, David.
Yeah.
Is it good? Am I getting the right idea if I say that the concept web helps me make sense of the numbers? Like if I just started with a list of numbers, I could make different senses of them, but it would depend on how they get mapped from the concept web.
Yeah, that sounds right. This concept web says that like you're going to be tracking, like there's some memory locations in your computer that are tracking all these things, or little scrawls on a piece of paper that only you understand. But that because we like relate them to things that are more public, like number and like species name and stuff like that, we can start to we can make sense of those kind of random scrawls by how they map into parts of the world we do understand. And so yeah, so the main thing we're trying to get to today, and I'm having a little trouble like connecting it, but basically what we're trying to say is that when we apply our example functor E to our concept objects in our concept web, we get these kind of we get all the examples of that concept. But what I want to say is that the Yoneda lemma says instead of applying E to something, what you can do is map in from generic elements, generic species, generic species over time intervals, generic things that make Priya happy or whatever. And that gives you the same answer. So that's what the Yoneda lemma is about. So maybe I'll move into that unless there are other questions.
Just one clarifying question from what you just said. What was the verb you used? You said the Yoneda lemma says we can something on the generic ones as opposed to the examples. What was it that we could do?
Yoneda says the examples of some concept are the maps or the overlays of the generic of that concept. Generic to all examples. So you have your set of, like, this is very poorly written. I apologize for that. We have our examples, and then we have these things called generics. And if we map our generics onto the examples, this is generic of the concept. So let's try this again. What it really says is E of some object C is Hom from the generic on C to E. So it's kind of weird. Like E over here, we're like applying some functor to C, and we're going to make sense of this. Don't worry. This is the goal of the talk is to make sense of this. What I'm writing here. But over here, we're mapping. So in one sense, we're applying, and on the other hand, we're mapping. And what we're mapping in is a generic for C. So what is the generic species? What does it mean to be a generic species? What does it mean to be a generic can of soup, right? If you have cans of soup, they all have sizes, they all have soup inside of them, they all have a label. A generic one is a can with a size and soup inside and a label. That's a generic one. I don't have the actual label. I don't have the actual soup inside. I don't have the actual size of the can. Those are all variables, and leaving those as variables is what the generic is. And the Yoneda says that if you take that generic can of soup where the size is unknown and the label is unknown and what soup is unknown, and you kind of map it on to your set of examples of all the soups you have in your life, then that can will map to a can in your cupboard that you'll like kind of overlay it on there. You'll overlay the abstraction. And then once you do, you'll overlay the label that you see there. Like the generic label will become the actual label, and the soup that was generic will become the soup in there. And that by all the possible overlays of the generic one onto yours are exactly all of your cans of soup.
It seems to me like there's it's trying to say that some diagram commutes essentially. You can either do the evaluations first and, for each example, or you can map the generic properties and then first, right, amongst themselves, like the relationships that the generic properties have, and then evaluate, and basically you'd get the same answer in every case, something to that effect. I know it's being very vague what I'm saying, but is that roughly in the right direction?
I think so. It's not that something commutes, it's that you have all the examples you have, but the generic can of soup is itself like creates examples of things. Maybe that's what we need to say. So for example, yeah, so if you have like if you have a child, and every child has as mother a woman, say, and has as father a man. I don't think that's controversial. Oops, that's supposed to say a man. So then when you write down the generic child, it has a generic woman associated to it, namely its mother, and it has a generic man. So you could write down all of the, maybe we should do this example. So we could either do this example or the example of graphs. And does anyone have a preference? Would you rather see graphs and the Yoneda lemma in that setting, or this example and the Yoneda lemma in this setting?
Well, let's do this one since you started it.
Let's do this one, yeah. So we start writing down we have our database of childs, all the childs we know, and
Can I interrupt for a moment?
yes, please.
So Tim has a comment, like he says, like, if the species were wolves, like the same table of population over time could make Priya happy because of the population growth, but make ranchers sad because the herds are thinned, feeding more wolves. So two different O-logs, but the same data.
Mm,
Does that make
nice.
sense? Yeah.
Yeah. Yeah. Okay, so maybe Alice has mother June and father does anyone know any men? Okay, let's use them. Okay, Niels, I guess. And Bob has Priya.
Okay.
And Ted. And Carl has Larissa. I hope this is okay. I don't even think. And I guess I'm next. Okay. And then etc. So this is what's a woman's name? Maybe Carla is Deb's mom, and maybe Bob is Deb's dad. Okay. Although maybe that's, yeah. So what we didn't do is, so everything here is a person. Okay. So maybe, yeah. So, okay, let's see what happens with this. What is the generic? This is like all the examples I have. Oh, I also have a woman. I have a table full of women. And maybe it has people I haven't said yet, but each of them is a person. So maybe it's got Alice, Carla, Deb, Larissa. But then there's also got people we haven't named yet. Sophie, I don't know. And each of these is a person, and they have the same name as a person that they do as a woman, let's say. Anyway, so we start to do this, and we do this for man, and we do all this stuff. And we have all these people. And right, so what is the generic child? What is the generic child? So this diagram commutes. Does anyone have a sense of what a generic child is? So this is like my examples. These are like all the people I know in the world. And this is a functor from C to set. Does everyone see that? If this is C, then E taking C to set will assign a set to child and assign a set to man. And this is the person, everyone can create their own O-log. So if you don't agree with this, if you don't think a child has as mother a woman, because sometimes the person's mother doesn't identify as woman and you want to care about that in your O-log, then that would be your conception of the world. And so this will just be mine for this moment. Doesn't mean it's mine for all time. But so in this conception of the world, the examples that I know of that I'm tracking are these. And that's how I'm seeing the world, and that's how I'm tracking all the examples of everything I know. And when I meet a new kid, I put them in here and in my mental database, and I write down their mother and their father. And maybe I don't know their father yet, so it's just kind of like if this is I don't know, Phil, then this could be Phil's dad. It's kind of generic. And that's what I mean by generic, is just filling things in the most generic way. So the generic child is called child. and their mother is child's mother, and their father is child father. And then there's this, we know that the diagram commutes. So does anyone have a sense of where I'm going with that part? What is that going to say? If this diagram in C commutes, then what other parts of the database will we need for the generic child? That makes sense? So the generic child, y to the child, is also a big database full of information. But this database full of information is much different. It's not like all the examples I know, like this one. It's the generic child. So anyone have a sense of what I should do next? I think I'm losing people.
Where does the where does the person thing comes here, like in the table you wrote?
Yeah,
Like
exactly. Exactly. So let's put in a woman and what person they are, and a man and what person they are is I think I should have labeled these is a person, is, yeah, I don't know, something like this, is person. Okay, so we all now to make our generic child, we made a generic woman called their mother, and we made a generic man called their father. And so the only woman we know of in this very basic generic thing, the only woman in the whole world is child mother. And the only man we know of in the world is child father. And why did I say they were the same person? Who let me say that? That's terrible.
Yeah, that's where I was confused.
I am so sorry. I don't know why I thought they were the same person. So most people's mother and father are not the same person. And so the diagram does not commute. Yeah, the people who, yeah, I don't know any children whose mother and father are the same person. So child mother, the person is child mother. And the person for child father is child father. And so we also, I forgot to write this, but we also have a person table. And in the person table, we have all the people we know of. I guess there's another person we know of, which is that the child is a person. And so I should have put that into child name or something. It's child person. Sorry, this is a bit hard to read. Oh, sorry about that. So person is the last one, and it has, what am I drawing here? How do I draw these things? I take every object in here, every square, and I write out all the outgoing arrows. And there's 3 coming out of child. So those are the 3, I forgot to put it here. So is, and then like Alice, but this would be like Alice as person. And this would be Bob as person. It's not Bob as a child. So Bob is a child, but Bob is also a person. And when you look at Bob as a child, you get extra things about them. You get to know their, maybe what kindergarten they go to or whatever. Whereas when you look at them as a person, you don't have all the same data about them. You have less information about them. So we can look at Alice as a child or as a person. And that's kind of what I should be writing there. And similarly, the child's mother is a woman, but we can also look at that woman as a person. And changing your viewpoint is something that you can do with this. So we have the child as person. We have the child's mother as person. This tiny, sorry about that. And then child's father as person. And we're done. So this generic child is not something that grows over time. Like our examples, we might keep adding to, whereas the generic child is just what the database schema C, what this concept web C says childs have. every child has a father, a mother, and is a person. And that data is what this has in it.
So this says every child in the world will have all these data.
Yes, but not only that, this is so E is a functor from C to set, but Y child, Y is for Yoneda here, is also a functor from C to set. What does it do? It takes every object C and assigns it the, I don't know how commonly used this is, but it assigns it all the ways of getting from a child to C. Like, what are all the C things you can derive if you have a child? You can derive a number that's their height. You could derive a number that's their weight. You could derive their first name, their last name, etc. This is all the things. If C is the object called like first name, then this would be, or strings, this would be all the strings of letters you could derive knowing a child. You could know the string of letters for their first name or last name, or etc. But in my little concept web, there is no string object. There's just these 4 objects. And so all I need to do to track the generic is track the just kind of ugly database here of like what is needed to have a child: a father, a mother, and a person that is the child. So any questions about this?
David, there is a comment in YouTube which Niels posted. So Limo Utan asks, what about genetically engineered child from X chromosome of a woman and X chromosome of a man, but all remain person or a clone?
Yeah. So again, in all this stuff, it's your OLOG. It's what you want to ontologize the world as, and that can change over time. And this is what I'm doing. And you could say, oh, I've got a different one. Some children have 2 women parents, and you really want to track that, and that's important to you. Then you make your own OLOG, and that's the whole point. The point is that this is like that. Sorry, that's the point of the kind of categorical viewpoint on this thing, is that you shouldn't have one perfect OLOG that is for all time the case. You should be willing to change your OLOG as you learn about the world, and then have functors between them that let you take all of your old examples and map them to new examples, or take all of your new examples and see what they would look like in your old schema. And if you have a schema and I have a schema, and we think of children as different things, we still might be able to map between each other and say like, oh, when you say child, you mean a child conceived in the usual way or whatever, as opposed to through genetics. Okay, I can take your data and understand it. Yeah. So
Thank you,
here's,
David.
yeah, sure. So so what we need to do, I always make this bigger and bigger. What we need to do is see, understand the mappings between the generic and the. So the point is that if we take this generic thing, and it's too ugly, I think. Okay, let's see if we can do it. So what if we took this generic instance Y child, and we like overlay Y child on E.
David, I have a question for that. So when you said like mapping the lowercase c to C child comma C, like, so we have this concept web, which is the mathcal C, and like
Yep.
when you write the lowercase c, how do I find that in the concept web? Is it like a box in the concept web, or is it
A
like
box.
something? Yeah, okay.
Little c is a box, and this says Y child of mother, because mother could be a C, would be all maps in C. Some people write HOM, from child to mother.
Okay.
Okay, so we go upstairs and we look. What are all the ways in here? I meant woman, sorry. What are all the ways in here to map from child to woman? So we look up here and we say, ah, there's exactly one way. and is called has as mother, right?
Mm.
And so in our generic, as our generic applies to woman, we're supposed, I guess that's over here, we're supposed to write child has as mother, and I abbreviated child mother. But we're just writing that Hom set. We're writing in woman all of the ways that in C we can get from child to woman. Because the generic child has how many women in their life? One, a mother, in this olog. And how many men do they have in their life? One, the father. And so that oneness is what C is saying are the maps from child to woman.
Okay.
Okay, thanks for the
Thank
question.
you.
So now we have these two different databases, one with all the examples we know, and that's E. And it's got Alice and Bob and Carla and all these people in there. And then we've got this other one called Y child, which is the generic child. But both Y child and E are functors from C to set, the same C. They both have what they call child. They both have what they call mother. They both have person, woman, all these things. So we could overlay the child one on the other one. What does that mean? It means that I want you to take child and put it anywhere you want. I want you to take like everything in this guy, in a child, and map it to one of these things. And then I want you to take this one and I want you to map it to one of the mother ones. And I want you to map this one to one of the father ones. But I want them to all agree. Like if the child's mother in this database was called child mother, then in this database, whoever you sent the child to, their mother should be who you sent the mother to. And that's what's called a natural transformation. Does that make sense? Questions about that? So the Yoneda lemma is about natural transformations. Yoneda says, natural transformations from generic on C to arbitrary E is E of C. So it says, if you want to take everything in this database, this one here, and map it to something in this database, such that children go to children, and their mothers go to their mothers, and their fathers go to their fathers, and etc., then the only way to do that is to map child to one of these people here. And when you do that, like you're mapping the generic onto its referent, if that makes sense. So I think I could try to do this again with graphs, and then maybe we would see it, or maybe there are questions. I've kind of said the whole thing that I wanted to say, that like the only way to do it now is the compassion of seeing who's lost and who's not, and what needs to be said to get it across. Because we could, like, if you want to prove the Yoneda lemma, like what you do is you just kind of follow your nose, and you basically concentrate on the identity, and you think, okay, what's going on with the identity? What's going on with the identity? What does this property say about the identity? And you keep doing that. But it's both really nice to do that because you learn how much weird stuff you can get out of just looking at the identity and how it satisfies everything about the Yoneda lemma. But it's also kind of boring because every single part of it is extremely basic. Like you're just like, oh, well, yeah, the associative law does that. Oh, yeah, the unit law does that. And you just use all the parts of category theory, and each one ticks off one box that you need to tick off to prove the Yoneda lemma. Right. But we don't want to do that here because it's too much. It's just too rote. It's too simple, and also takes a really long, takes probably 20 minutes. So instead, we want to just get the idea, which is that like overlaying a generic onto something is the same thing as applying the functor. Applying E to child is the same thing as, yeah.
Um,
I have an idea, if there are no questions, which is to try y of a different thing, y of woman, to see that if we do the generic woman and we map them into here, we would get not that we would get the set of women, but yeah.
So just to confirm on the proof, you're basically saying that the proof is straightforward but requires a bunch of work.
Yeah, the proof, you sit down to prove the Yoneda lemma. You remember the statement, you write it down, and you look at it, and you say, okay, how am I going to do this? And there's an isomorphism. There's that E of C, applying E to an object, is a Hom set from something to something else, from the generic on C to E. And you say, okay, well, how am I going to prove this isomorphism? Well, I need to prove two directions. I need to prove that if I have an element of E of C, then I can get a map from the generic on C to E. And vice versa, if I have a map from the generic on C to E, I need an element of E of C. And so you say, okay, how am I going to get, I'm going to pick one of those two ways. How am I going to get that map? Oh, finally, at the end, you're going to need to show that the round trips are identity. But let's talk about those two maps. When you're trying to figure out those two maps, you just say, okay, I know I'm supposed to think about the identity. What do I do? And you think about the identity on little c, and that gets mapped somewhere, and you start following your nose. And it's quite straightforward and like helpful to do this. Yeah, it's definitely a worthwhile exercise.
It's a good exercise to make sure you know the definitions at least.
It just checks that you know the definitions, and you're just going to use associative law exactly once here, and you're going to use unit law. Like all the little parts of how a category is built come in. You compose with something on the right over here. You compose with it on the left over here. Like you can compose, if you have F, G, and H, you can compose G and H over there, or F and G over here. And like, well, if I do F, then G, then H, it doesn't matter which order I did it in. And that's the sort of thing that you just see come up in front of your eyes as you prove this thing. But what it really is all about is that generic, like it's kind of about these generic objects. Yeah. So if we, what is Y woman? Can anyone tell me Y woman? I need a big, well, that's probably not big enough, but I need child and their mother and their father and who they are as a person is person. Then we have woman, and they're all people, and a man, and all men are people, and then our set of people. Okay, so what are all the maps in this schema over here from woman to child?
There is no map.
There is no
woman
map.
to-
So
Yeah.
this is empty. This database, this table full of children, the generic woman does not have any children associated to her. So, okay. And then what are all the maps in this thing from a woman to a woman?
It seems to be none.
It seems to be
Identity.
not in the graph, but of course this is supposed to represent a category. I shouldn't say of course, but that this thing is supposed to represent a category, not just a graph. So it does have the generic identity. So we could write identity here, ID sub woman, or we could just write woman. I don't know which one is like pedagogically better, but as long as we have one element of the set, we're happy. And then what is the woman's person? Well, it's the woman as person. And what does the generic woman say is, what are all the men in a generic woman's life? Apparently there are no men in a generic woman. We know of no men. We don't have any men that every woman is associated to. And so we would come over here and we would have empty again. And then person, we'd have woman as person. That's the only person in a generic woman's life. And so the point is, if we overlay this thing on our examples, E, sorry, so tiny, I have to do this. So if we overlay this on this, what we need to do is take every child and put them at a child. Well, that's There's no data there. And we
Mhm.
need to take every man and put them on a man, but there's no data there. That overlay is trivial. But we do need to take our woman and overlay her on, our generic woman needs to be overlaid on an actual woman. And so we have to take this woman and put it at like Deb or whatever, or Larissa or whoever we pointed to. And then that person would need to go to the person that Deb or Larissa or whoever is. And so when we overlay this on our examples, the only ways to do that is to put this identity element at one of the women we have in our examples. And so no matter whether we pick child or woman or man or person or anything in the schema, the generic one of them, when you overlay it on any example set, will be the set of examples of that concept. And I think that's kind of the end. So I think we just need to like talk about it in any way that's comfortable. We could do another example, but it's basically, that's kind of the idea.
Thanks, David. I have a question.
Yeah.
Okay. So I really like how you concluded it, saying like the number of ways I mean, please tell me if I'm wrong. The number of ways we can overlay the generic over the non-generic thing is the same as the number of examples, right? And so when I read Yoneda lemma in a formal sense, this doesn't come out. But when you say it, it's like, yeah, this is how things should be. Like it makes sense. But what do I do with this? Like, how does Yoneda lemma help me, like in understanding the world?
In understanding the world?
Or how do I use this idea? Like, how is this idea useful? Can you give me some examples? Is that a dumb question? I don't know.
No, it's not a dumb question. It's a matter of whether when you say useful, you're talking about what you care about. So what do you care about that you would want to use it in? Like, do you mean like in math, how is it useful in category theory? Or do you mean like in the real world when we think about populations and stuff?
Yeah, in the real world, maybe like when we keep track of databases and stuff, like how can we use this concept?
Okay. In databases, yeah, I don't know if someone said. In databases, you can use this to, basically queries, if you say, I want a man and a woman with the same favorite book or something like that. This is a different database. Imagine you're a dating site and you want two women with the same favorite book or whatever, a man and a woman with the same favorite book. And what you do is you can take the generic woman and the generic woman and take their favorite books. Now you get two, but glue those favorite books together so that there's one. And that would be like a co-limit of some maps. It's like there's like the generic book, and then it maps to the generic woman by the generic woman's favorite book, and it maps to the generic woman by the generic woman's favorite book. And you push those out and say that you want the books to be the same. And then a query will be a map from that thing into your database. So you have this database with 100,000 entries in it. And now you have this little teeny database called Two Women with the Same Favorite Book, and it's got like 7 entries in it. Just 7 little things in it. And you just want to map those little things over to your big example set, and such that everything commutes, in other words, a natural transformation. And when you do, you'll find all pairs of women in your database with the same favorite book.
David,
Thanks,
this is exactly though what I had in mind earlier when I mentioned that it feels to me like a commutative diagram, that you do something, it's the order, you change the order in which you do things, and practically speaking, it simplifies things. Like it's much easier to do, as you say, the pushing out first in the generic case, because you have a lot fewer examples and then map those, rather than do all the examples and then do the filtering there. Does that make sense?
I think so. It's also saying that maybe for ordinary reasoning, not just in databases, that in terms of what you're saying, Ted, about simplicity, that what we should do when we reason is reason about generic objects. Because like our example set has billions of entries in it with like all the songs and all the song lyrics and all the stuff we've ever heard, all the stuff we've ever seen. And it's too much stuff. But if you look at the generic, instead of like querying your database of examples and working with the results of those queries, like, okay, think about all the flowers I've ever seen and whatever. It's too hard. Instead, what you should do is think about generic flowers and generic things and put them together and think about how those behave, because it'll be a simpler reasoning. But we'll get the same examples once we map it in later to our example set. We'll get the same outcome. It's just that we don't have to do it immediately. Like, we can simplify our thinking. I think that's a good way to think about it, Ted.
I had
So Tim
question.
asks,
Oh, I'm sorry.
Mhm.
I had a question. I don't know if it's a good time to ask. That relates a little bit back to Edmund's question, and your clarification of the proof and the isomorphism involved in the typical proof of this lemma. I'm wondering if, first of all, it makes perfect sense the way that you said it, but there's a finiteness to this argument that seems almost by definition, because you're talking about databases. And so I'm wondering how it, well, I'm wondering two things. So let me say them, and maybe you can answer them together. Maybe they're really flip sides of the same coin. One is how foundationally important this finiteness is. In other words, what if the examples were in the continuum or something like that, right? Like where there isn't a listing to be had. It's not a database. And then the other thing that I've been thinking about that might be related is how important in the sense making that you've been trying to convey to us is the understanding of the proof. In other words, am I, because there are different proofs that one can come up with, for example, but do they lead to different senses of what this means?
No.
Right.
There, in some sense, there's not many proofs of the Yoneda lemma. Like, maybe you would say, okay, I wrote it with this font and you wrote it with that font, or I did it in this order, you did it in that order. But like, there really is just, I mean, it's really a checking thing. And why is it important? It's important because there's a difference between being carried on your parents' shoulders through the hike and walking the hike. There's just a difference. And if you're always carried on the shoulders and you think, okay, I've heard about the Yoneda lemma, I got it explained to me, etc., you don't know that your legs can do it. And there's something very important about walking your own walk. And this one is simple enough, but like, it's going to take you, even if you kind of speed run through it with if you're tutoring somebody but you know what you're doing, it'll take at least 20 or 30 minutes. If you don't know what you're doing, it'll take like an hour. It could take an hour. But as long as you keep your eye on, I just need to keep looking for how the identities are operating and stuff like that, that once you do that, the confidence you get from that is too important. Like, I think doing that exercise, if you want to be in category theory, doing that exercise once is important, knowing that you can do it.
Right. That's absolutely right. And very appropriate for our compassionate math, idea. I guess where I was going with it was to link it with an earlier conversation you and I had months ago about the relevance of the proof to the sense-making mechanism. So in other words, I conjecture that it might be possible, the flip side of what you said might be possible, where in walking it yourself, you get lost in the weeds because you pay attention to all the local steps and you fulfill all the requirements, but you don't get a global sense of why that is, like the actual sort of understanding that you try to convey to us through, these specific examples. And so I wonder how you see, speculatively, I guess, as a matter of the practice of compassionate math, that relationship between the two, because I agree with both of the things you said, but I just wonder how you link them.
Yeah, it's interesting. Yeah, you walk through the Yoneda lemma and you prove every single part of it, and you say, oh, okay, wow, there it all is. What did I just do? And you're staring at it like, yeah, what is all that stuff I just checked, and which part of it is important and which part isn't? I think knowing that you can do it means you know that any example you actually work out next, any part of it that you get confused in, you can go look and see your proof and see like, oh, this is what I'm supposed to do. Oh, of course. Yeah, of course. Okay, here's what I do. And then you think about it and then you understand it. So it like, what am I saying? By working it all the way through, by walking it yourself, you the intuition can come a little later, because you can kind of speed up your process and see, you can stop seeing all the weeds and all the places you got lost, and start to clean it up, and start to see what it is about this that is tracking something interesting. Like, it's not, I don't know how interesting, like, yeah, it's about this idea of generic, and how are you saying, kind of, how would you know that if you hadn't had someone tell you, or would you?
Yeah, no,
Yeah.
that's exactly right. You said it right. So for example, I'm trying to contrast in my mind the sense told, like you kind of told us a kind of sense of this, versus the sense made from an explorer's perspective, from Yoneda's perspective, let's say, when he first discovered it, or someone who happens upon it just by exploring databases or whatever.
Yeah. Yeah. I mean, I think what we do is we try to account for it. That goes to something that Priya said, I said last time, apparently, was that for me, sense making comes from accounting for things. So we have all these pieces everywhere, and we're like, how do these pieces cohere? What am I supposed to do with this? How can I say something about this that, how can I put these all together in one seeing? It's too many disparate pieces. How do I account for all these pieces? And that struggle, I think, is something that that every person does. Like, even babies, they're like, oh, why am I seeing, like, oh, that's my hand. Like, they have to make sense that that's their hand, right? They see the pieces, and they feel themselves somewhere else moving something, and they're like, oh, that piece moving in front of me is related to what I'm doing with my hand, like internally with my proprioception. So how do you link all these pieces together? What are you supposed to, what's supposed to go with what? All sorts of stuff like that. That sense making is a pretty magical thing that I don't think we really understand how we do it, but it's something we do all the time. Like, I'm talking and talking, right? Oh boy, like, so much. I feel like I'm saying a lot of words, but some people are nodding along, and like, because you're not hearing all the junk, and you're hearing the stuff that I'm trying to say. And same with that, your proof of the Yoneda lemma. You can look at it and say, like, okay, that was a stray mark. That was me going off to the side a little bit. What's really going on here? What is it really about? And as you take the time by yourself, and after you're done with the proof, looking it over for a while, you can see how it makes sense. And it'll be your very personal thing.
Running the risk of, I certainly don't want to dominate this, and I'll stop after this, but because it's a little bit of a dialogue, and maybe you'll take it just in this way. I wonder, because again, as part of the compassionate math initiative, we want to foreground the multiplicity of perspectives and types of understanding. So when we talk about sense making, what comes to my mind is that there, in some ways, each one of us, as you were saying, is a great example, right? We're trying to understand the sense behind the words that you give us. I'm willing to accept, in fact, I think most likely this is the case, that the actual sense inside of each one of us is different, because it's conditioned on our priors, on where we come from, and so on, the vocabulary we're used to. Yet there is a compatibility, presumably. Like, the more we listen, we adjust, each one of us in some way, but there is a certain compatibility condition which feels compositional, feels categorical, feels like, what you're trying to say to us here, that even though we have in some ways always distinct senses, but they fit together somehow. Is this making sense to you? Yeah,
that makes sense. I imagine, like, I'm saying some stuff, and each one of you guys has your own riverbed, your own, like, kind of riverbed system, with, like, where it's shallow, where it's deep, and stuff like that. And I'm talking, and it's running water through your system, and your system is, like, overflowing over here, and, like, maybe making a new path over there, and whatever. And each person is doing a different thing. But because I'm talking for a little, like, long enough that you give me this slot to talk, there's something that's kind of repeating over and over, and the thing I'm trying to say is going to, like, make its own pattern in each one of your minds in some sense. Some part of it is going to be shared. And I think what we're looking at here is that, like, when I see the world, I see it like this. I see it like there's a child and a mother and stuff like that. And that's how I've embedded and grooved in what I've got. And Tim was saying that he's got, you know, children who have two X chromosomes from the same mother or whatever thing, or from two different women. And that's part of what he wants to see, right? And so we've each grooved in, we've been exposed to the same stuff in our life, maybe like slightly different, we maybe very different backgrounds, but we've seen similarities of what the human condition is, and we've grooved those in our own way. And there's something in common between those, which is what lets us talk to each other. But there's also something different, which lets us disagree with each other, I guess, or have something to talk about.
Thank you, David. That's quite a beautiful concept. I'm beginning to see more things from our previous conversation, more than what we had in our previous conversation. So we have two more questions in the chat, but before moving on, like, I want to thank you for the great talk. So let us thank David. Like, I'm gonna put a clap here. I'm searching for, yay. Thank you, David. So yeah, is it okay if I share the questions like from the chat?
Sure.
Yeah, okay. So Tim asks you, if there are two concepts that distill to the same Yoneda lemma, what does that mean? Is there something we can infer?
Yeah. So let's say you have two generics, and they're both as a generics, they're isomorphic. You find this isomorphism between one and the other. Then the two concepts, each was a concept in your original graph, right? Because that's what we mean by generic. We have this category, I called it a graph, but I meant category. And we have these two concepts in it. And we take the generic of the first one and the generic of the second one, and we find there's an isomorphism between them. Then it turns out that those two concepts were isomorphic in the original category. There was a mapping from woman to female person or whatever thing, and a mapping from female person back to woman, and they round trip to each other. And round trip means compose, you get identity. And so if they're isomorphic as generics, then that'll be the case if and only if they're generics in the schema itself. But that's called, some people call that the Yoneda lemma, that a certain functor is fully faithful, but it's really more of a corollary of the one I showed.
So the O-logs are isomorphic. They're conceptually the same, or they are the same.
No, not
concept.
the O-log, not the O-log. The O-log is this big, is the big thing here. Oops, the O-log is like this whole thing, but the generic might have been this one here.
Oh, okay.
And there might have been another one, which is like a young person.
Mm.
And a young person is a child, and a child is a young person. The only way that the generic child and the generic young person could be isomorphic, in the sense that I think Tim meant, is if there was an isomorphism already in the schema C.
So it's an if and only if.
If and only if, yeah.
Great. Thank you, David. And then we have a comment from the YouTube from Limo Mutan. He says, isn't a generic person also a generic child? So the generic women does have more than one identity. So, but also as mother, ditto man or father who may not be in the finite table. Does that make sense?
I don't think a generic person is not a generic child. So I'm a person, but not a child. And the only way a generic person could be a generic child would be if every person was a child. So I think I didn't understand, like, I think that very first sentence made me feel like I didn't understand the question, or that the questioner was missing something. But a generic child is a person. If that's the direction we want to go, we can go that way. Does the question make sense if we go that way?
Yeah, the question is going the other way. Isn't a generic person also a generic child, which is not in this diagram you drew?
Right. If every person, you could say every person has as inner, quote unquote, a child. Every person has an inner child or something like that. Right. But the child's inner child, a child and a child is themselves, but a person and a child is not themselves or something. So, oh, maybe, oh, I see. Laressa's saying, I think they're saying that every person is the child of someone. I see. Sorry, it makes much more sense now. When I wrote a child, I was thinking of a young person as opposed to a kid, like the offspring. So this olog would have to be every child is offspring, and or whatever. I don't know what's offspring. And every person is offspring, and then offspring also has a mother and father, and etc. We could just keep building this thing. So let's try to get. Let's see if we can understand the question. Can you say it again, Priya?
Yeah. So the question goes like this: isn't a generic person also a generic child? So the generic women within stars does have more than one identity,
Yep.
also.
That's right. So now that a woman is a person and a person is an offspring, and an offspring has a mother, which is a woman, and that woman is a person, and every person is the offspring of somebody, and that offspring has a mother, then now all of a sudden the generic woman has many women in her life, herself, her mother, her grandmother, etc. They also have father and grandfather and paternal grandmother and all these things. And so now we get something that is infinite in the sense that Ted was worried we were avoiding before. It doesn't have the continuum. We could have something, as big as the real numbers, but that doesn't come up automatically in these settings. But we do have infinite databases with a woman, her mother, her father, her grandmother, her grandfather, her other one. And that generic thing, even though it's infinite, if we map it into an arbitrary set of examples, will just, even though there's infinitely many women now, it'll still pick out just one woman. Like if we overlay that on something, the identity woman, the generic, will land somewhere. All of her mothers and fathers and all these other things will land where they need to go, and they'll be completely determined. And so it still works, even though the woman has more women in her life than just herself in the new offspring case.
And this is because it's a natural transformation. Is that right? Like
the natural transformation is what forces that we have this generic woman, and then all this list of all these other women, her mother, her grandmother, all this stuff. And we're saying now we're going to overlay that big thing on our examples. And so we have to pick a place for the generic woman's mother, father, grandmother, all these things. But we also have to pick a place for her to go. And we think we have too many choices. Oh, it's so annoying. Where are we going to put the mother? Well, no. Once you decide where the identity goes, where the generic person goes, generic woman goes, all of her other associated things, her mother, her grandmother, they are all carried along deterministically. They all overlay onto that woman, Carla, her mother, and her father, and all that stuff.
Cool. Thank you, David.
Sure.
I think Nona had a question.
And yes, that part is the naturality, is the fact that they have to overlay like that. Yeah.
Thank you.
Sure.
Hi.
Hi.
I have a question about generic relationship. We have a violence relationship. In this relationship, we have a victim and we have a perpetrator. And there is an incident like an physical violence or emotional violence or something. And how can I generate this?
So we have a violent act, we have a perpetrator.
And we have a victim.
Okay.
And there is an incidence in this relationship, like physical violence or sexual violence or financial violence or something else. That can we say an incidence?
You mean like the type of the violent act? I think you want maybe, I don't really know incidents. To me, when I hear incident, I hear like
Yeah,
a
yeah.
certain time when one happened. But it also sounds like you want to talk about type, a type of violence. And every violent act has a type.
Yeah.
Yeah.
And how
And
can
then
I generate the,
what do you say?
how can I write this violence relationship generic, like a child generic?
But do you want a generic physical violent act, or do you want a generic violent act?
Yeah.
Which
Violent act.
the generic violent act? The
Yeah.
generic violent act would have perpetrator, victim, and type. And the violent act would be called violent act. Maybe it's just called V for short. V.perp, V.victim, V.type. And that's the whole generic. It just has what it needs to have because we didn't have any extra stuff. So this is the generic. And if you had your database full of all the examples of all the violent acts you've seen, then if you map, the Yoneda lemma says that if you overlay this thing onto your database, then it'll send V to a particular violent act, and it'll send the perpetrator to the actual perpetrator and the victim to the victim and the type to the type. And all the ways of overlaying this will be all the ways of seeing violent acts in your database.
Thank you.
Sure. Yeah.
Thank you, Nobuo. Do we have more questions for David? Okay, if there are no more questions, I have a question for David. David, like, what makes you excited about Yoneda lemma? If I may ask that.
Well, when you're doing category higher, like not higher category, but if you're doing category theory, it moves application. It lets you not have, it lets you treat functors as objects and not think of them as things that apply. Yeah, it lets you treat the analogy as an object as opposed to something that does something. And once you see it as an object, you can start to probe it with other objects. You can start to look at how it interacts with this one and that one. And the generic, really, the idea of generics and the Yoneda lemma let you change your viewpoint mathematically in a way that lets you just work with category theory the way it was meant to be worked with. It's meant to be worked with in systems where you look at the mappings between things and the translations between things. And if functors both live in a world and apply to something, then it's like a little bit like they have two roles. One is to be in a world of functors and one is to apply to something. But we just want everything to just be in worlds of relationships. So we don't want them to apply. We shouldn't need to make them apply. So when it comes to Yoneda lemma and functors to set, which is the most common kind of base way we study things, we say that in that setting, we don't need to apply anymore. We just need to look at the maps. So so why I like Yoneda lemma is mainly for what it does in math, but it does have in category theory, but it does have this kind of way of looking at it that some people get excited about, that a thing is known by its relationships. That I personally don't think that's correct. A lot of people are like, the Yoneda viewpoint is that everything is known by its relationships, and there is some truth in that, but the relationship that makes the most difference in the Yoneda lemma is the identity. And so an object is really its identity is more like what it's saying. And that's kind of a little bit less surprising than saying it's all of its relationships. In some sense, they're right. So I'm not trying to disparage that point of view, but like some people like the Yoneda lemma because it feels like it's saying that everything is known by its relationships. And there is really truth in that. But the most important relationship is your relationship to yourself in that setting. Like it really is the one that makes the proof go. Yeah.
That's lovely. That's a lovely explanation. part of my question, like my previous question also came from that. It's like when you put it this way, it feels so natural and simple. Why do we have to know this like explicitly, and how do we use it? Like that's where my question was coming.
That's the whole, okay, for me, that's the whole point of category theory, is that we want the most obvious stuff to be tracked.
Lovely. Cool.
Because what happens usually in most parts of math is they want the obvious stuff to stay in people's mind. And they want the math just to track the hard stuff. But in category theory, the math is tracking the easy stuff. And the point is that when you put enough straws of easiness onto something, it gets very, very heavy. Like if every step is easy, but you do a million of them, then like in the end, you actually did something quite big. But Yoneda lemma is trying to track something that feels obvious anyway, which is that the way generic things work is that they kind of overlay onto particulars.
But it is also
tracking. Say again?
But it's also it's something obvious, but also very important.
Yeah. By making the obvious explicit, it lets the math carry all of the load instead of having some of it stuck in yourself. And that way you can let the math kind of skate on its own rails instead of you having to hold it all the time. All the intuition is actually in the symbols now. The idea of generic objects is in the symbol itself. It's not this why child thing is carrying genericness of woman, right? Why woman or why child. And that the fact that you don't have to carry it anymore is kind of why it works, I think.
While learning polynomial functors, I learned it's quite powerful to do it, like to keep track of this obvious thing.
Yeah. So the category theory point of view is not like in some sense it's compassionate again, which is that if people get lost, it really is not a good feeling. And category, it's pretty easy to get lost, but it's also, if you're tracking, it's easy to get found again. If you make sure that every one of your steps has been a small step, you can just kind of recover like, okay, no, wait, like what's going on here? You can think about it and you don't have to track it in your mind. You can track it in the symbols.
That's lovely. I think this is the most, for me, this will be the important message, like we're tracking the obvious and most important thing, that category theory allows us to do that, and paying attention to those easy steps, but keeping track of them and accounting for them is quite powerful thing to do. Yeah. And the lemma is like one of the epitome examples of that. Thank you, David. All right. I think, yeah. And Larissa says she wants to thank you for letting her know about this session. And it was so insightful and interesting to witness. So witness the talk. Thank you, David. So let's all thank David again. Thanks for the great talk and staying back for answering our questions. And yeah, thanks a lot, everyone, for participating as well.
Thank you, David.
Yeah, thank you, guys.
The talk is recorded and it will be available for everyone in the YouTube Relatorium channel. Thank you.
Bye, all.
Have a good weekend. Bye.
Bye.
Bye.